Good morning.
Good morning.
Okay, Mr. Miller, I made you a host. I hope I didn't make myself not a host. No, we'll see.
Oh, you did.
Yeah, I Googled it. Okay, let me.
Hello.
Hi. Oh boy. I hope I haven't messed things up. Let me just see. Okay, I made Mr. Miller a host, but am I still a co-host? Only the host can share. Okay, so I don't want to do that. Let's see. So how do I okay. How do I change that? Okay, I'm gonna end the meeting and then go back, all right, so that this gets undone. So just hold on a minute. Oh, I can't end the meeting. Mr. Miller, could you end the meeting, please? I didn't make you a co-host, I made you the host.
Oh,
Okay, so end the meeting for everybody, and I'll go back and start it again.
all right, where's
It's where, so upper left-hand corner.
Oh, sorry. There it is. Oh, it's on the bottom right for me.
Oh, okay.
Okay. All right. I'll see you in a little bit.
Yeah, everybody has to rejoin. Okay, good. Y'all are better at this than I am.
We are having technical issues. Please hold on.
Yes, thank you. Okay. Okay, well, let's see. All right, so I'll work on that again. Okay. Let's see. Somebody asked about the first exam yesterday. And I said it'd be a schedule, but no, it won't. Because I looked at my syllabus, and whoever asked that, thank you for that question. I looked at my syllabus, and the first exam is scheduled for September 11th, which is a week from this Friday, okay? And you will have only handed in one homework at that time, and that's not enough to give you an exam over. So I'm going to push the exam back to September 18th. hope that's okay with everybody. I haven't figured out how I'm going to give it to you yet. I'm investigating the possibilities now, but we may do some practicing beforehand. Okay, I think that's the only announcement I had. Let me check my notes here. Yeah, I believe so. Okay, yeah, so first exam moved from September 11th to September 18th. And you will get a new homework assignment Friday. It will be a little bit longer because of, well, all the mess with the storm and everything else. But okay. Any questions from you guys before we start? Miss Britton, I think you said something, but you're muted.
Mr. Britton.
Yeah.
I thought you said Miss.
No, Mr. No.
Sorry, my internet's never very good, and it's especially not with the storm having come through. It's still not going right. I'm not sure if the tower's messed up or what.
Right. Yeah, this has been hard for everybody.
Yeah, your video just keeps freezing on my thing, but it doesn't really have any problem on when you do the actual work.
Okay, yeah. Oh yeah, these technical problems. Well, okay. Well, it helps that you get the notes every day and you get the recording every day.
Mm-hmm.
Okay. So let's start talking. We're going to start talking about, well, derivatives today, which goes by other names. So I'm going to share my screen. Okay. Can everybody see my screen?
Yes.
Good.
Yes, ma'am.
Okay. Okay, let's see. This example kind of got away from me, but I want to sort of talk about, yeah. Okay, so here we are. So let's take this problem. A ball is dropped from the upper observation deck of the CN Tower in Toronto, and that's 450 meters above the ground. We want to find the velocity of the ball after 5 seconds. Okay, so we have this problem. Now, where do we start? Well, Galileo, 4 centuries ago, did a lot of experiments, and he came up with a little formula. Said that the distance s of t fallen by the ball at time t will be equal to, okay, 4.9 t squared, where t is in seconds and s of t is in meters. Now this is what you call a little model. And for one thing, it completely ignores air resistance, okay? But it's what we're going to use. It's a pretty good approximation, especially if your distance being fallen is not that far. And it's, yeah, which ours is not, 450 meters total. Okay, so we're ignoring air resistance, wind, and things like that. But we're taking, as a rule, the distance fallen, S of t is 4.9 times t squared, where t is time. We're measuring t in seconds and S of t in meters. Now, this doesn't say anything about velocity, but okay. Average velocity okay, you've learned before, distance equals rate times time, right? So that means that your average velocity is, which is a rate, is a distance over time. Average velocity is the distance traveled divided by the time elapsed. And we can get average velocities while the ball is falling. So our idea, what if we take a small time interval, say 5 seconds to 5.1 seconds, and compute the average velocity over that time interval? Have more people entered the waiting room? Did you all see a sign come up for that?
Yeah.
Yeah, okay, let me
Yeah.
go back. Let me go
How do
back.
you?
Let me go back. Let me make sure I let people in, especially since things got messed up. Okay, stop broadcast. All right, participants. Okay, yes, there were 2 more. All right. Okay, Mr. Miller, I'm going to work on this co-host thing, but I apparently don't have it down yet.
That's fine.
Well, it would be a real plus if I could get you to do the admitting, and I don't have to go back and forth. And I'm also going to figure out how I can let you guys, all of you, share your screens. I Googled that too, but enough experimenting for one day right now. We want to talk about the math. Okay, so average velocity is the total distance traveled over the time elapsed. Okay, so we're going to take a time interval from 5 seconds to 5.1 seconds, and we're assuming, I guess, the ball hasn't hit the ground yet. Let's compute the average velocity over that time interval. Okay, so the average velocity on the interval 5 to 5.1 would be, okay, distance traveled at 5.1 minus distance traveled at 5. So that would get the distance traveled over the time interval 5.5 to 5.1. And the length of the interval is 0.1. 5.1 minus 5 is 0.1. Okay, so let's put that in our little distance formula. Remember, it's S of t is 4.9 times t squared. So I'm just sticking it in that. So that's going to give us 4.9 times 5.1 squared minus 4.9 times 5 squared divided by 0.1. Well, I can factor up that 4.9 out of the numerator. And that gives me, so 5.1 squared is 26.01. So I got then in the top 4.9 times 26.01 minus 25. 5 squared is 25. And that's all divided by 0.1. Well, when you divide by 0.1, that's 1 over 1/10. And
So it's technically 10 times 4.9 times 1.01.
Yes. I just took the 0.1. Yeah, here from here to here, 1 over 0.1 is 10. Okay. And multiplying all that out, you get 49.49. So the average velocity on that little time interval was 49.49 meters per second. Now that's small in time interval, very small. And we got the average velocity on that time interval. Well, let's take smaller time intervals around 5. Okay, so we just computed this first one, 5 for 5.1. And okay, I'm going to spare you the computations here, but I'm just plugging in numbers, except I'm going to do this one out. Yeah, well, by plugging into doing this sort of thing, okay? But at the interval 5.01, instead of putting 5.1 up, it put 5.01 in, and so forth. Average velocity is 49.049 meters per second. And if I take an even smaller time interval, these are all numbers that are larger than 5, these time intervals, 5 to 5.001, I get 49.0049 meters per second. These are all on the right. And let's take at least one on the left. Okay, so the interval from 4.999 to 5. And okay, I've got that, but I actually wrote out the computation here. On 4.999 to 5, the average velocity is, okay, it doesn't really matter whether I put the 5 or the 4.99 first, okay, as long as I keep it consistent, top and bottom. S of 5 minus S of 4.999 over 5.5 minus 4.999. Well, okay, the denominator is 0.001s, 1,000. And the numerator then is 4.9 times 5 squared minus 4.9 times 4.999 all squared. And then again, I can factor out that 4.9 in the top. Okay. And then I've got 25, 5 squared, 25, 4.999 squared is 24.990001. I did pull out my calculator. And 1 over 1,000th is 1,000. Okay. 1 over 1/1,000 is 1,000. So I just put that in the numerator, and then that's going to give me, okay, 4,900 times 9.999 times 10 to the minus third, which is, okay, doing the arithmetic, I come out with 48.9951. Okay, so to the left, there's one value over a time interval from 4.999 to 5. So looking at these numbers, okay, kind of looks like, well, these are numbers coming in from the right. These are numbers coming in from the left. It looks like they're getting close to 49. And yes, they are. And in fact, we didn't, okay, this is doing some numerical approximations, but we can actually figure this out, okay? We've been taking limits and we've been doing things a little more sophisticated than just getting numerical approximations. Okay, so what we really want here is the limit as t approaches 5 of S of t minus S of 5 over t minus 5. That's what we were doing in each of those time intervals above. And what was I going to say? Oh, I'm not recording. Let me go back. Okay. Let's see. Please, somebody remind me to record.
Honestly, we can't see if you're recording or not on our screens. So we couldn't know if you are or not.
Okay, so. Oh, Mr. Okay. Mr. Flores is also recording this, so he's going to have the whole thing. It's good to have a backup.
Also,
okay, now
I do know that at least on my screen, which I'm on a computer, it does have a flashing dot up in the top left-hand corner for which it says recording. At least when we're in this screen right now, I don't quite know if it carries over to when you're screen sharing though.
Oh, my screen, it doesn't show it when I'm on this screen, but okay. Let me go back and check. Okay. It says recording. Okay. On this screen. So it is recording now. Okay. So we want to find the velocity at time 5. What we were doing there when we were doing these numerical approximations was taking smaller and smaller time intervals about 5. Okay. That's a limit. We've been talking about limits. It's a special kind of limit. What we need is the limit as t approaches 5.
Excuse me, Miss Kenny. We can see your screen.
You can't?
Yeah, I can. It's in black.
Okay, you can or you cannot.
I cannot. We cannot.
Cannot. Oh my gosh. Okay.
Yeah.
Okay, thank you. I need to know that. I must not have done it correctly. Sorry for the technical difficulties this morning. Okay, can you see it now?
Yes, ma'am. Yes.
Yes, ma'am.
Okay, good. All right. So what we really need here is a limit, and we want to take the limit as t approaches 5 of s of t minus s of 5 over t minus 5. Okay. So actually, what that expression in the red parentheses is the average velocity over the interval from t to 5, and I don't know whether t's bigger than 5 or less than 5, divided by t minus 5. So that's average velocity. Oh, wait a minute. Excuse me. No. It's the distance traveled. Okay. This is the distance traveled over the interval from 5 to t. Okay, and I don't know whether t's bigger than 5 or less than 5, divided by the length of that interval. So that is the time elapsed. Okay, so it's distance traveled over time elapsed. For every t, you're getting that. You're getting the average velocity for every t. Well, we can just take them all at once and take the limit as t goes to 5. Well, that's equal to then, the limit is t goes to 5 of 4.9 times t squared minus 4.9 times 5 squared over t minus 5. Again, I can factor out the 4.9 in the numerator. And then you've got t squared minus 5 squared over, and then that's all over t minus 5, still a limit. And this will factor. So I can rewrite t squared minus 5 squared as t minus 5 times t plus 5. And now, okay, I've got t minus 5 as a factor in both the top and the bottom. So I can cancel the t minus 5s out. And once I do that, once I cancel the t minus 5s out, my 0 over 0 problem is gone. So now I'm down to the limit as t approaches 5 of 4.9 times t plus 5. My 5s and my s's are a little bit hard to distinguish, aren't they? These are 5s. So, okay, now once I'm down at this step, the 0 over 0 problem gone. Once I'm down to there, I can just plug in direct substitution. So I put in 5 for t, and that's going to give me 4.9 times 10, which is 49. Okay, so it looks like the velocity after 5 seconds is 49 meters per second. Okay, and we computed it exactly. At first, we were looking at small time intervals around 5 and getting average velocities over those small time intervals. It looked like the average velocities were converging to 49, but using our algebra and computing the limit, we can see that it's exactly 49. So the ball is traveling at 49 meters per second when t is equal to 5. And that's not an average velocity. That's what you call an instantaneous velocity. Okay, any questions so far? Okay, don't hear anything, so I'm going to go on. We're going to make this a little more precise. We're going to make a definition. Suppose f is continuous on some interval containing the number a. And actually, again, f doesn't have to, no, the interval doesn't actually have to contain the number a. So continuous everywhere except the number a. That rarely happens. For the most part, f is going to be continuous on the interval. Okay, but we're going to define the instantaneous velocity, or the velocity at a. Okay, I was doing this morning. That's why I was kind of late and was misbehaving. I don't know where that stupid little line came from there. Okay, it appeared, or know where those letters came from. But okay, we're going to make this definition. Instantaneous velocity, or the velocity at a, is v at a is a limit as t approaches a of f of t minus f of a over t minus a. Okay, so the velocity is a special kind of limit. And okay, oh goodness, I'm sorry. Back to our ball. We found that the ball is traveling at 49 meters per second when t is 5. What if we wanted to know how fast the ball is traveling when it hits the ground? Well, first of all, let's remember our little model. S of t is 4.9 t squared, and you're dropping the ball from a height of 450 meters. How do I find when the ball hits the ground? Can somebody tell me?
Could it be when S of t is equal to 450?
Yes. Very good, Mr. Levy, I think. Yeah, the ball hits the ground when 4.9 t squared, which is S of t, is 450. Well, okay, that says that t squared is 450 over 4.9, and that means that t is plus or minus the square root of 450 over 4.9. Well, the minus here makes no sense, right? The ball's dropped at time 0. So I'm going to throw that away. The only time that makes sense for us in this problem is the positive t. Okay, and well, that's going to be an irrational number. I did some arithmetic, factoring and so forth. That square root is 30 times the square root of 5 over 7, but that's approximately 9.6 seconds. That little squiggle means approximately. And I'll try to be real careful about that. Well, all right, this is a model. It's not a perfect model, so you're not getting precise information out of it anyway, but we're taking it, you know, as what we're using. So this is an exact number. This is an approximate number. It is useful to get decimal approximations, but for the most part, I want you to leave your answers on your homework and so forth in exact form. Okay, but let's compute the velocity at 9.6 then. That would give us the velocity when the ball hits the ground. And of course, once the ball hits the ground, the whole thing changes. That S of t is 4.9 t squared doesn't apply anymore. I guess, well, it depends on what the ball hits, but if for the most of the time it would bounce. And then you need another model for that. But okay, but until it hits, our S of t is 4.9 t squared is a pretty good model for the distance fallen. And the velocity then at 9.6 would be the limit as t approaches 9.6 from the left. Okay, from the left because I don't know what happens from the right when the ball hits the ground. Okay, so these are times from the left, but computing this limit, okay, again, it's 4.9. Okay. Inside the limit, I've got 4.9 t squared minus 4.9 times 9.6 squared over t minus 9.6. Factor out the 4.9. And then I can factor t squared minus 9.6 squared. I did that, both of those in one step. Okay, just like we did before. And then I've got t minus 9.6 over t minus 9.6 as a vector in both the top and the bottom here. Okay, so I can factor those out. And okay, so when I do that, 0 over 0 problem is gone. Oops. So now I'm just down to computing the limit as t approaches 9.6 from the left of 4.9 times t plus 9.6. And now I can just put in 9.6 for t. Once I put in the 9.6, the limit's gone. The limit sign is gone, okay? When I use my direct substitution property. So I get 4.9 times 9.6 plus 9.6, which is 4.9 times 19.2, which is, okay, I'd use my calculator, which gives me the fraction form of the answer, which I've got to figure out how to switch the mode, but I can switch that over to a decimal fairly easily by just multiplying the top and the bottom by 4. So that gives me 94.08 over 100, which is 94.08. So when the ball hits the ground, the ball is traveling at approximately 94 meters per second. So we computed the instantaneous velocity at time 5 seconds, and we computed the instantaneous velocity at time 9.6 seconds. What about any time in between? We can do that too. So consider this question: how fast is the ball traveling at any time A in that interval from 0 to 9.6. 0 is the time when you drop the ball. 9.6 is the time when it hits the ground and the whole situation changes. But anytime between 0 and 9.6, it's just falling freely. And according to our definition, the velocity at time A, or the instantaneous velocity, as opposed to the average velocity, instantaneous velocity at time A is the limit as t approaches A of s of t minus s of A over t minus A. Okay, oops. And that's equal to the limit as t approaches A of 5.9. Oops, it's not 5.9, it's 4.9. Okay. 4.9 t squared minus 4.9 a squared over t minus a. And that's equal to the limit as t approaches a. I can do the same thing as I've done several times here this morning already. Factor out the 4.9 in the numerator. And then I can factor t squared minus a squared. Okay, why is it doing this? Let me go back to the top. Let's see if I can get it to stop that. Oops, nope. Been very contrary this morning. iPad has an attitude. Okay, now it's out of that. All right, so this is the limit as t approaches a of 4.9 times t minus a times t plus a over t minus a. And now I've got t minus a as a factor in both top and bottom. And that's going to be the limit as t approaches a of 4.9 times t plus a. Notice that, okay, right here is where you got rid of your 0, 0 problem. When you divided out that factor of t minus a. And now I'm ready to take the limit. Okay, so I'm going to put in a for t. And that's going to be 4.9 times a plus a, which is 4.9 times 2a. And I'm just doing it again. This helps sometimes. This is equal to 9.8a. So the velocity at time t equal to a is 9.8 a meters per second for 0 less than or equal to a less than or equal to 9.6. Any questions? No? Okay, let's do some more examples. I'm going to change the function from this s function, distance function, and it's doing this don't know why.
Excuse me, Dr. Kennedy. I don't know if
Yes.
take a break now, but there was at least one other person in the waiting room.
Okay. This would be a good place. Okay. Don't know who CJE is, but okay. We're at 8:40. All right. Thank you for telling me that. Okay. Let's do another example. So we're through with our tower and the ball falling. And I'm just going to take a function.
Sorry again, but I don't know if you're screen sharing right now, but we can't see your screen.
You can, okay. I think I
We're having a lot
forget.
of fun this morning.
Yeah, I forget to do it correctly. All right, so screen. Oh, because I was just going directly. I gotta start broadcast. Okay, I'm forgetting to do that. Well, I apologize for all the technical problems this morning. Okay. All right, suppose this is an example. F of X, oh, let's call it T, at least this morning. F of T is equal to 1 plus 2T minus T squared. Okay, this is just a function. Find the velocity function V of T for this function. Okay, so we want to use our definition of velocity that we had sometime before here. Why is it not letting me scroll down? This works better. All right. So according to my definition, V at, okay. Well, I want to get it for any time T, but I would need a T approaching A, so I need another letter. For a time A, velocity at A is the limit as T approaches A of F of T minus F of A over T minus A. That's how we defined velocity, instantaneous velocity. Okay. And okay, the reason I need to call that time A and not T is because I'm letting T represent the number the numbers that are getting close to A, but are not equal to A itself. Okay, so my function has changed here. My function is now 1 plus 2T minus T squared. So now I have the limit as T approaches A of 1 plus 2T minus T squared minus, okay, F at A is 1 plus 2A minus A squared, okay, all over T minus A. Okay, and if I tried putting in A for T right now, well, I would get 0 over 0. Okay, so that's meaningless. If you get 0 over 0, that means you need to do more stuff. It means you don't know anything 0 over 0. If you get try it. If you get 5 over 0, that means you'd have no limit. But okay, 0 over 0 is totally meaningless. It means you don't know. So I need to do some algebra here, right? That means, let's see, this is the limit as t approaches a of, okay, well, I've got 1 there and I've got -1 there. So that's just going to add out. And let's see, and then I've got 2t there, and then -2a there. Okay, remember that minus carries through because it's 1 plus 2a minus a squared is in parentheses. Okay, so that takes care of the 1 and the 2t stuff. And then I've got the t squared stuff. Okay, so I've got minus t squared, and then that's really plus a squared because it's minus minus. All right, well, that cleans it up a little bit. And let's see. Keep going with the algebra. Okay, I've got 2 times t minus a from that term. And this one, okay, I'm going to take it step by step, but I'm going to write that as minus t squared minus a squared. So the plus now is a minus because I put t squared minus a squared in the parentheses and there's a minus outside. But the nice thing is I can factor this. Okay, I can factor this, so now I have the limit as t approaches a of 2 times t minus a minus t minus a times t plus a all over t minus a. But now I can factor a t minus a out of the numerator. So yeah, because there's a t minus a there and a t minus a there. So that's t minus a times 2 minus t plus a. And I still have that denominator of t minus a. Ah. And now, okay, now I can't cancel until I have products on the top and the bottom. Well, on the bottom, I've got t minus a times 1, but now I can cancel. And once you cancel, the 0 over 0 problem is gone. So this is the limit as t approaches a of 2 minus t minus a. And now I can do the direct substitution. 2 minus a, put in a for t, and I get 2 minus 2a. So all together, okay, and that's right, okay. All together, velocity at time A I wonder, my iPad gets very hot when I'm doing this. It's using a lot of energy. Maybe that's the problem. Velocity at time A, V at A is equal to 2 minus 2A. Okay. Any questions?
No, man. I think we're good.
Okay. Well, notice, for one thing, given a function, f or g or whatever, the velocity is another function. The velocity for that function is another function, okay, which you get by computing this limit. And this is also called the derivative. Okay, we'll talk about that tomorrow. It's a rate of change. Velocity, yeah, by computing this particular limit, you are getting a formula for the rate of change of the function. It's a very important idea, the rate of change. With the pandemic, we've been hearing about rates of transmission and getting the rate of transmission down below 1 per person. Okay, so down below one person infecting 1. That's really important. That's talking about a derivative. It's a rate of change. It's a velocity. And it's talking about this idea. Okay, so a very important idea comes up everywhere in physics and engineering and, well, all over the place. Epidemiology, that's been real important recently. I think this is a good stopping place. I apologize for the multiple technical problems today. I'm going to keep trying and see if I can't get better with this, but let's go back to the Zoom screen and stop broadcast. Okay. So, any questions before we end class?
No, I think we're good.
Okay, well, I'll see you tomorrow. We're going to keep talking about this idea of velocity and rate of change, and also start using this word derivative. Okay.
Okay, hope things work out better soon.
Me too. Me too. It's so distracting. Okay. You know, when I get finished teaching every morning, well, basically I teach from 8 to 9 and 9 to 10. I'm just exhausted. But I got to get used to it and manage all this technology and manage it better. So
Miss Kenny, I do have a quick question. When do you know when our first exam is going to be?
yeah, I talked about that at the very first of class. Were you the one that asked about moving the exam back yesterday?
No, ma'am.
Okay, well, somebody did, and it was a good question because I looked at the syllabus. The first exam was scheduled for September 11th, which is next week. That's too soon. That will only cover one homework, the one that you are handing in on Friday. So I'm moving the first exam back to September 18th. Okay.
Okay, thank you.
Okay, so you have a homework due this Friday. You will have a homework due next Friday. The exam will cover those 2 homeworks. Okay. Okay, anything else? Then bye. If you want to stick around for a second, if you've got another question, I'd be glad to answer it. So